Okay, good morning, class. Welcome back to Physics for Future Presidents. Is this really, really loud? Or is this okay? It's okay? Good. Thank you. Okay, so last time we started studying Newton's laws and we discussed Newton's first law. Remember, Newton's first law said that objects in motion tend to stay in motion, objects at rest tend to stay at rest unless acted on by an unbalanced force. We're going to be moving on today to discuss Newton's second law, but first I just wanted to give a couple of reinforcements of Newton's first law. First is that this exciting demo, that ball is there at rest. That ball is undergoing a state of constant motion. It's pretty boring motion, right? But it is a state of constant motion. It's moving with a constant velocity of 0. Okay, but that is a constant velocity. So this ball is not being accelerated, which means all the forces acting on it are balanced. Okay, one important thing to remember about velocity and acceleration is that velocity is a speed plus a direction. Okay. And an acceleration occurs whenever the velocity is changing. Okay. That change can be either a change in the speed, which is what we normally think of when we think of acceleration, or it can be a change in the direction. Okay, so let's do another simple demo of this just to make a point about acceleration. Okay, here I've just got a ball on a string, another exciting demo. We'll get to better ones later, okay? But I'm going to start spinning this ball, okay, above my head. So the ball's moving in a circle. It's moving with a constant speed. So you might think it's not accelerating, okay? But it's constantly changing its direction of motion, right? It's going from moving to the left of the room, to the back of the room, to the right of the room, okay, as it moves around a circle. So the ball is being constantly accelerated when it moves in this motion, which means that it's being acted on by an unbalanced force, okay? In this case, the unbalanced force is the string itself that I'm holding it with. Okay? The string itself is always pulling the ball towards the center of the circle, and it's constantly accelerating the ball, but it's accelerating in this sort of unique way where the speed is staying constant, but the direction is constantly moving. Okay? But this is absolutely accelerated motion. So if you see motion like this in a circle, you know that the object is being accelerated. Okay? Anytime that the direction of motion changes for an object, it's undergoing acceleration, not just when the speed is changing up or when it's moving down. Okay, so let's jump in and start discussing Newton's next law, Newton's second law. Let's see how the boards are going to be blocked today with these demos. I'll try to stick over here for now. Okay, Newton's second law just tells us how an object moves if it is subject to an unbalanced force. Okay? Newton's first law tells us that if an object is not subject to an unbalanced force, that it doesn't move at all, that it doesn't change its motion, its velocity stays constant. Newton's first law tells us that if there are unbalanced forces on an object, then the object will accelerate due to those laws. So let's just write it down since it's a pretty important law. Unbalanced forces will accelerate an object. Okay. And it tells us another piece of information which is really key, which is the more mass of the object, the smaller the acceleration. Okay, first let's think about the first sentence. So, unbalanced forces acting on an object will accelerate the object. So, by accelerate, we mean that the object can either speed up, or it can slow down, or it can change directions. Any three of those is a form of accelerate. Okay? The second one is so intuitive that you might find it really simplified or a little bit crazy, but the more massive the object is, the smaller the acceleration. That just means it's harder to push heavy things, right? More massive things. So that's not too complicated. That's great. So let's write down that intuitively. Massive objects are harder to push. Okay, so Newton actually quantified this a bit in terms of the acceleration, and we're going to do that here very briefly. Remember that the mass is the measure of the inertia of an object. It's the definition of mass. How hard is it to move an object? That is the inertia of the object. Okay. And Newton found this relationship between the unbalanced force that the unbalanced force acting on an object is just equal to the mass of the object times its acceleration. Okay. Force, the unbalanced force is equal to the mass of the object times the acceleration of the object. Okay. You've probably seen this equation. If not in class, then you probably see it in science fiction movies. It pops up on blackboards sometimes when they're doing deep physics equations. It's just that force is equal to mass times acceleration, okay, the famous equation from Newton's first law. We can turn this around a little bit and write that the acceleration is equal to the force divided by the mass, which just once again reinforces the really basic concept that if you apply a given amount of force, the more mass of the object is, the smaller the acceleration is, right? So the bigger this mass is, the smaller the acceleration of the object is going to be. So I think that's very intuitive. So I will only repeat it about 10 times. But the more massive the object is, the smaller the acceleration. Okay, so let's talk about our first very specific force, and that is gravity. Gravity, our first force. Okay, gravity is so important we can't get rid of it. It's always in the world around us unless we go out into space. Okay? But as long as we're here on the surface of the Earth, we always have to deal with gravity. So let's talk about it a little bit. So it's so special that we have a name for this force, which is just the weight of an object. Okay? This is just a special name for gravitational force. And in case you didn't catch that, let me reinforce it once again. That weight is just a force. Okay? Weight is the force of gravity pulling down on objects on the surface of the Earth. Okay, so Galileo, back before Newton's days, Galileo did a series of experiments, and he proved that if we could get rid of air resistance, that all objects falling to the surface of the Earth would have the same acceleration. So this ball, when it falls, it drops with a given acceleration. Okay? It's speeding up as it drops to the ground. Okay? We know from everyday experience that that ball isn't going to drop at the same speed as, say, this sheet of paper, right? It's because, not because the gravitational acceleration is any smaller for the sheet of paper than the ball, but it's because air resistance is having a much greater effect on the sheet of paper than it is on the ball, and it's pushing it back up. If we get rid of the air resistance, then these should, at least from Galileo's experiments, fall at the exact same rate. That acceleration is completely independent of the shape of the object, the size of the object, or the mass of the object. Right? Every object falls towards the surface of the Earth with the same acceleration. Let's do a demonstration that was done on the moon during the one of the Apollo moon missions. But here we're going to do it. We're going to cheat. We've got a tube here. Let's see. Are we zoomed in on this? Perfect. Okay. So this is a vacuum tube. So in a minute, I'm going to suck all the air out of this and try to see if Galileo is right, that if we got rid of the air resistance, that objects would fall with the same speed. Right now, there are two things in here. There is a coin, which is heavy, and we know from experience that a coin isn't going to have much air resistance. Right? It's a pretty heavy, dense object. It's going to fall pretty rapidly. And there is a feather, which we also know from everyday experience is going to be subject to much air resistance. It's going to fall a lot slower. So if we do this, let me flip this over. Ow, it's not child-proof, okay, or professor-proof. Okay, so I'm going to flip this over. Let's see. So you can hear the coin falling. Okay? Can you actually see up there the feather fluttering down slowly? Is that obvious? Okay, so let's do the experiment, which Galileo couldn't quite do, which is we're going to suck all the air out of this. If I can remember how this pump works. Okay, so I got this hooked up to a vacuum pump. And we are going to pump this down. Okay. I'm going to close this off here. I'll put this back off so you can actually hear me. So I've removed about 99% of the air in this tube. Okay? So this is a pretty good vacuum. It's probably actually about comparable to the vacuum on the surface of the moon when the astronauts were there. The air is gone. There should be no air resistance. Okay? So let's see what happens when we let these things fall together. So pretty close. At least you don't see any evidence of fluttering, right, in that feather anymore. It's falling at the same acceleration of that coin down towards the surface of the Earth. Okay. One more time, just because it's fun. Okay, so with the lack of air, everything would fall with the same acceleration towards the surface of the Earth. Brilliant, brilliant observation by Galileo. He did his with a series of ramps and balls rolling down the ramps, and he could change the characteristics of friction and basically showed that as he improved the system more and more, everything was accelerating at the same rate independent of the size or shape. Okay, so let's put a number on this acceleration. Okay. The acceleration due to gravity. And to be specific, this is the acceleration due to gravity here on the Earth. Okay. The acceleration due to gravity is equal to 9.8 meters per second squared. This is the rate change of the speed when an object is falling. For our purposes, let's just say it's 10 meters per second squared. That's close enough. Okay. So when an object is dropped, this means after the first second, it'll be moving at 10 meters per second. After the second second, it'll be moving at 20 meters per second. After the third second, it'll be moving at 30 meters per second. Okay, so each second it's picking up 10 meters per second as it drops. Okay. This acceleration, since it's common to everything falls at the same acceleration towards the Earth. We give it its own symbol, little g. So little g is the gravitational acceleration near the surface of the Earth. Okay. Now, we already saw that force is equal to a mass times the acceleration from Newton's first law. And we know that weight is a form of force. It's the force of gravity pulling down. We know the acceleration. Acceleration is little g, 10 meters per second squared. Okay. So we can, specifically for weight, we can relate the weight of the object to the mass of the object. The weight is just the mass times the acceleration due to gravity. Okay. These are, of course, often used interchangeably in everyday speech, and you'll hear me use them interchangeably, even though I don't mean to. I'm trying to be careful about it. Right? Weight and mass of an object. Right? They are two very different things, so I want to be clear that you need to keep these two concepts separated. Okay? Weight is a force, of course, and it is specifically how hard gravity is pulling on an object. And the mass is a measure of inertia. That is how hard it is to accelerate an object. Okay, we use them almost interchangeably because they are related by this simple relationship. Okay? And this relationship is simple because the acceleration due to gravity is the same for every single object on the surface of the Earth. We will talk about this later in the semester, but that's actually fundamentally a really bizarre thing. It doesn't have to be that way. The fact that everything accelerates with the same gravity towards the surface of the Earth has really important implications for the physics of gravity itself. Okay? But you could imagine if you had two objects of the same mass, but gravity did not accelerate them at the same rate, they would have the same mass and different weight. And then we would never, ever get confused between using weight and mass interchangeably in common language. Okay? But the world around us has this relationship. It's simple. That's probably good. Physics homework would be a lot more difficult if it wasn't that way. But we'll talk about the more fundamental implications of that later. First, we wanted to focus on the motion of objects and get that down. Okay, special time. First quizzes. Yes. Yeah, applause. You guys have your quiz slips? Yeah. Did anybody not bring quiz slips? Yeah. Do you guys have any really nice neighbors around you? Can we switch to the computer projector? Thanks. Okay, anybody still not have quiz slips? Raise your hands. Oh, good. Okay, first thing, remember to put your name and your student ID on these. We want to give you credit for taking this quiz, for attending class. Okay. And then the second is circle the number of your discussion section. Okay? And if you can't remember your number, I have lots of clues on here, including date, time, and your GSI name. So if you can't figure it out from that, then just write a note on there, and we'll figure it out for you this time. Okay, quizzes are going to be, just so you know, they are counting towards your grade. They're going to be 2 questions. The quiz is actually worth 3 points. The first point is just for turning the quiz in. That's to make sure you're attending lecture. And then you get 1 point for each one of the quiz questions. So let's start with question number 1. Okay, suppose you are at a stoplight and realize that an important antique physics textbook sale, that's a strange one, ends in 5 minutes. Naturally, you start off very rapidly. To you, some papers on the dashboard fly straight backwards. To an observer on the ground, they, A, move backwards rapidly, B, move forward rapidly, C, remained where they were, or D, fell straight. So by observer on the ground, you're thinking of somebody like walking to the crosswalk and just watching you as you accelerate away. Dashboard, that's the section up above you where the air vents are. So in front of you where you sit when you're driving a car. That's right. A, B, C, or D, mark it. Okay, next question. Suppose an ice skater is moving on the surface of a frozen lake at a constant velocity. What is true about the external outside forces acting on the skater? There could be some, but they all cancel out. Gravity can be ignored. They are all perfectly horizontal. Or D, there are none. Okay, I think that's enough time for that question. You guys pass your slips to the nearest end of the rows. Make sure your name's on it and your ID number, and the GSIs will come up the sides and collect them. Can you guys help collect on this side? Awesome. Okay, remember to bring your quiz slips.
You say weight is kind of force, right? Does that make weight factor?
Maybe. Pass your quiz over and I'll talk to you about it. Okay, one of the points of the quizzes actually is that your GSIs are going to look through them and grade them, and then if there are any major misconceptions in the quizzes, then they'll address those in the sections, of course. So, okay, let's move on. Oh, I have a couple of announcements before we move on. So. First is that so the first essay question is now up on BSpace. So there's some more over here, guys. So there was an essay question 0 that was posted, which was just an example. The first actual essay question that is due is in the assignment section, and that is due Sunday at 5 o'clock. So that is 6 hours before your homework is due at 11 o'clock. Okay? It's not a very long essay. It's only 200 words, which is half a page. So we had that due earlier on Sunday than the homework because we want the GSIs to be able to read through your essays in order to be prepared for the discussion. So the essay topics will sort of guide the discussion section discussions. And so we want to get some of your input in that beforehand. The other reason we're doing the essay questions as well as the Wiley Plus questions is because your midterms and your final will have both. And so I didn't want to pop essay questions on you on the midterm and not give you any for homework, because I'm guessing you probably wouldn't like that very much. So you'll get some feedback on the essays from the weekly homework as well. So just remember that those times are different. And that the essays are done on BSpace. They're done directly in BSpace. You just type your essays directly into their little text tool there. And of course, the Wiley Plus is done on that system. There's this issue about student IDs and putting them in on Wiley Plus. And we'll get that resolved. So I sent out a chat message. I have a different view of Wiley Plus than you guys do. So I think we might have resolved that. But pay attention to the announcements on the forum, and we'll get that resolved soon. Okay, so let's go back to Newton's first law. And let's talk a little bit about accelerated motion. Okay. I don't want to go into it in much detail, just because I think it's very intuitive, at least at the level, certainly beyond the level that we're going to approach in this class. But accelerated motion, if it's not changing the direction, it means it's changing the speed. And when you drop an object like this ball, okay, and it's accelerating downwards, it's going faster and faster and faster, right? The speed is constantly increasing. I think that is more than intuitive enough. So I am not going to dwell on that particular aspect too much. But there is a very important aspect about acceleration due to gravity that might not be quite as intuitive, and that is that the acceleration, the motion of an object falling in the gravitational field, is completely independent of how fast it's moving left and right. Okay, so let me say that again. When an object falls due to gravity, the rate that it's falling, the acceleration that it's falling, does not depend on the least on how fast it's moving horizontally in the gravitational field. Let's do a couple of demos to demonstrate that. Okay, the first one I've got here. Let's see. Let him get us up here. Okay, so what I have here in this little mechanism is there's a bar that's running through this little tube here, and it's cocked back with a spring. Okay? And I've got two metal balls on the ends here. Okay? One of them has, you can see, the rod is just passing right through it. Okay? And the other one is actually hooked onto the end of the rod. Okay? So what's going to happen is I'm going to pull this lever, and the spring is going to let go, and the rod is going to go shooting off to the right. Okay? When that happens, this ball, the rod's going to move out from under this ball, or through the middle of this ball, and it's just going to drop directly. Okay? This one, the rod's going to give it a kick, so it's going to go flying off to the right. Okay? So what I just claimed was that the motion of these things falling down towards the table is completely independent of how fast they're moving left or right. So if that's true, then these things should be hitting the table at the exact same time, independent of the fact that one of them is shooting off to the right and the other one is dropping straight down. Okay, so let's try it. Okay, you really have to listen for this one. Okay, so everybody listen close. And we want to listen to when the balls hit the table. Okay, so, very quiet. It's very exciting. Okay, did you hear? Let me do it again. So, if I can find, there it is. Let me do it one more time so you guys can hear that. Okay. Okay, this is the one that's going to drop straight down. This one's going to go shooting off to the right. Okay, everybody listen again. Okay. Okay, so they are falling at the exact same rate, completely independently of the fact that one of them is shooting off to the right and the other one is dropping straight down. There are a couple ways to think about this experiment intuitively. Okay? One of them requires major superpowers. So let's do that one first. Okay? 'Cause that's the funner one. Here are those two balls. So we've got this one, which is getting shot off to the left, and this one, which is just going to be dropping directly down. So both of them are accelerating downwards with g, the same acceleration. Okay? But in our first way of understanding this intuitively, let's just turn that gravity off. Let's imagine we have the powers to switch off gravity, and let's think about what's going to happen to these balls. Okay? So if we switch off gravity, this one's just going to go keep on shooting straight out. It's never going to fall, right? It's just going to keep on moving off to the left with the same velocity, but it's never going to change its height. It's just going to be moving off constantly to the left. And this one is just going to sit there. Okay? There's no gravity pulling it down. It's just going to sit there in space. So if we switched off gravity, neither one of them would be falling. One of them would be shooting off to the left side of the room, and the other one would just be sitting there. Okay? Now let's take advantage of our superpowers and instantly turn gravity back on, and all of a sudden both of them start accelerating downwards at the same rate. Okay? Both of them are sitting here. This one's moving off to the left, and boom. They both start falling down at the same acceleration. Okay? That's completely independently of the fact that that one is moving to the left. Okay? If gravity weren't there, it would just keep on moving straight off in a straight line. Constant motion. Let's do another way to think about this is to think about the idea of frames of reference. Okay? Frames of reference is one of those, can be kind of a complicated concept, but it shouldn't be. You should think about the frame of reference. Let me write this down. The frame of reference is just the worlds as seen by you. It is your perspective on how things are happening. Okay? So, Newton's first law holds in any frame of reference that is not accelerating. Okay. As long as you are not accelerating yourself, then you will see Newton's first law hold. Any force will accelerate an object with the subject to that relationship, that the force is equal to the mass times the relationship. Okay? Sometimes when you are thinking about problems, especially complicated problems, it is good to change your frame of reference to one that is easier. Okay? So let's think about this in terms of a very simple situation, which you guys have probably all experienced at some point or the other, which is you're on a bus or on a train or on the BART, okay? And you're traveling along at a constant speed, so the bus is not accelerating or it's not decelerating, okay? And you jump. Okay? You stand up in the aisle and you jump, right? If the bus is moving at a constant speed, you do not go accelerating backwards towards the back of the bus, right? You just feel like to yourself, in your frame of reference, you moved up and down. Okay? It was completely independent of the bus moving or not. Same thing if you have a ball and you throw it up. Right? If you're on a bus, you can play ball, okay, just as easily as you can sitting on the ground. Okay? If you're at rest on the ground. Okay? And that's because the acceleration due to gravity as you're moving, okay, does not depend on the fact that the bus or you or that ball has a horizontal component to your motion. Okay? The ball does not fall any faster or any slower than it would if the bus wasn't moving or the train wasn't moving. Okay? So let's do a demo of that here. This is the exact same thing, but in a little bit better setup, I think. All I've gotten here is a little ball. Okay? So we're going to shoot that ball up in the air. Let me do it once. There we go. When we're in the frame of reference of the train. So let's say this is a train car. Okay? we're sitting in that frame of reference. We're on the train, and we're watching somebody play ball. Throw that back to me, Butter. Thank you. Okay, so the ball shoots up, falls down. Okay. Nothing too surprising. Now let's do the exact same thing in a moving frame of reference. Okay. So now we're going to be on the ground watching this. Okay. Our friend is still on the train. They're playing ball, but we're watching them from our frame of reference at rest relative to that train. Okay. But to us, the situation will look a little different, but the ball is not going to fall any faster or slower. Okay. So, okay. Still goes up, still goes down, independent of the horizontal motion. Okay. It didn't get caught any faster or any slower because the train was moving. It was too slow. Give it a better push. Friction. Okay, so completely independently of the horizontal motion. Oh. My friend was sleeping. Okay, well, I guess I like that demo, but I guess it's telling me it's time to move on. Okay, so let's do another example of this, which is very famous physics demonstration, which is, let's see, I think I have to turn this on first, which is a big pole. Okay, so I am a hunter. And here is a little monkey in a tree. If I can get him up in his tree. Come on, monkey. Get up there, monkey. Let's see, maybe he doesn't like this demo. Let me go get my support. You guys, hold on a second. Ow. They didn't childproof this one either. Okay. I'm going to be back in 1 second. Don't go anywhere. Hey.
Before you can put the monkey up.
Oh, thank you.
Yeah. When in doubt, 1, 2, 3, 4. Yep. If the light's off, then you'll be able to put them on.
Okay, perfect.
Yep. Yep.
Thanks. Let's think today.
So, switch
Okay.
on power supply.
She's telling me to read the instructions.
Place the ball in the cannon.
Okay. I think it's okay. Yeah. Thank you. See, this is a lesson for you guys to always read instructions. There we go. Now the monkey is hanging in the tree. No problems. Yeah. This would probably be much better if I could read. Okay, so there's our nice monkey hanging in the tree. Okay, I am evil hunter. I like that monkey. And I have my gun here. Okay? So you see my laser pointer there. That monkey is not in a very good position right now. Okay? I think you're going to have to pan out vertically on this one. You can? There you go. Okay, so you saw that I'm aiming right there at the monkey. Okay, so this cannon, I hunt with a cannon, is aimed directly at that monkey. Okay. And I'm going to fire in a second. Okay? That monkey, though, is pretty smart. Okay? That monkey is watching me, and he's waiting for me to pull the trigger on this cannon. And when I do, he's going to drop, because he knows I'm aiming at him on the top of that tree. He's going to drop and try to avoid getting hit, because he thinks that he will drop in that and avoid the shot I'm aiming in his way. So let's see if that monkey is smarter than I am. Okay, how many people think that monkey is smarter than I am? That's rude. Okay, how many people know that I'm smarter than that monkey? Okay, let's see what happens. I think we are good to go here. Okay, eyes on that monkey. I'm going to fire. Monkey, I'm giving you warning. 3, 2, 1. Oh, let me check the aim again. There we go. Oh, poor monkey. Told you I was smarter than that monkey. You will never doubt that again. Let's do it again. I want to, and then we'll explain it after I do it in a little bit, do it one more time. So this time I'll read the instructions. Oh, looks like I just nicked the monkey. He's only wounded. He's climbing back in the tree. So, he still thinks he's smarter than I am. This is a really scary monkey doll, by the way. Okay, monkey's back in the tree. Okay, you might think I just got lucky on that shot, okay? That I was shooting it fast enough to that we could just ignore gravity for that. So let me turn down the speed on this a little bit so that I'm shooting at a smaller velocity. Okay. Going to take aim on that monkey. And I am set to go. So this time I'm going to be shooting the ball with a smaller velocity. Okay. So, well, let's see what happens when I do it. Okay, so 3, 2, 1. Oh! I think I was kind of behind the desk if you missed it up there, but I still got him. Okay, so let's, before I make something explode up here, let me turn these things off. And let's just draw this situation and talk about it for 1 second. Why do I still hit that monkey, even though the monkey's let go? And this is really easy to understand if we bring back our superpowers. Okay. So we've got me, the hunter. We've got that monkey up in a tree. That's about as good as I can draw a monkey. Okay. And here I am aiming directly at that monkey. So there is the bullet that I'm shooting at that monkey. Okay, to understand why that ball or the shot always hits the monkey, let's do our trick and turn off gravity and see what happens. Right? If we turn off gravity in this situation, the monkey lets go of the tree, and the monkey's just going to hang there in place, right? It's not going to drop. There's no gravity pulling it down. The monkey's just going to hang there. If I fire that bullet, the bullet's just going to move in a straight line, because I give it some initial velocity, and there's no gravity pulling it, nothing accelerating it. So it's just going to keep moving with the constant motion. Okay? So if we could pull off this trick of turning off gravity, I would hit the monkey every single time, right? So the trick here is that if we turn gravity back on, the monkey's going to start accelerating downwards, but the bullet's going to start accelerating downwards at the exact same rate. Okay? So both of them will start falling. Okay? The monkey is falling, but the bullet is falling as well. So independent of how fast we shoot that out, it's always going to hit the monkey. Now the caveat to this is if I were a hunter aiming at that monkey and I aimed at a straight line at that monkey, I would be a really bad hunter, right? Most hunters know intuitively, once they've hunted for a while, that they need to aim above the monkey in order to compensate for gravity and have the bullet bend down to hit. Okay? So turn gravity off. Think about the situation. Sometimes it's easy to think about things if you just can ignore some of the forces for a while. Okay, let's see. Where are we at? Okay. Let's talk about falling. We're going to talk a little bit about projectile motion. Okay? And in the famous words of Buzz Lightyear, all this is falling with style. Okay, projectile motion. The idea is that, or what goes up must come down, or how to play basketball if you've never played basketball before. Right? So when we shoot a basketball, we are giving that ball an initial velocity. And so we're giving it a start on its motion, and then everything that follows afterwards is just that ball falling in gravity. Okay? So let's, this is my basketball, okay, or tennis ball, or golf ball. Our first example of that is just going to be me throwing it up. Okay? Very easy. I throw it up. I'm giving an initial velocity in the upwards direction. Gravity is constantly accelerating it downwards. Okay? So it's going to go up. It's going to reach some maximum height. Okay? The faster I throw it, the higher it goes. Okay? The lower I throw it, the lower it goes. Okay? The faster I throw it, the higher it'll go up in the air. Okay? But all I'm doing is giving it that first initial velocity. Okay? After that, its motion is completely determined by the fact that it's accelerating in the Earth's gravitational field. Okay, so let's just draw a picture of that. Okay. I have a bad habit of losing chalk. Okay. So here, we're just going to throw this ball upwards. So I'm going to give it an initial little velocity in the upwards direction. Gravity is always pulling it downwards. so the first thing that gravity is going to do is start decelerating the ball because it's directed opposite the direction of the velocity. Okay? And then the ball is going to reach the uppermost point. So here's the trajectory of the ball. It goes up, okay? Comes to a stop at the top, and then it turns around and goes back down. Pretty easy, right? Okay. So when we're talking about projectile motion, all we're doing is giving a little sideways kick to this ball at the start as well, besides that initial vertical velocity. So if we throw that ball sideways, instead of throwing it directly upwards, we already know that the horizontal motion is not going to be affected by the gravity. So it's still just going to be moving at a constant speed, left or right. But its vertical motion is still going to be controlled by the fact that it's accelerating downwards in the gravitational field. Right? So if we give it, here's our ball. We're going to give it initial velocity. That is not vertical, so it's got a horizontal and a vertical component. Okay? Then we're going to throw it sideways. The ball's still going to go up because it's got an initial vertical component of velocity that's going to send it upwards. Okay? But it's also going to go to the side. Okay? So we've already seen this. Oh, I can't do this demo again. That's too bad. I did mention this is my favorite demo, right? Okay, you can think about this as our friend on the train. Friend has, never mind. The friend throws the ball, right? And the ball goes to the side as well as going up and down. So it's going to follow what we call a trajectory. Okay, so that ball is going to go up. It's going to come back down and hit the ground. And let's just put some names on this. This path that the ball follows is going to be called the trajectory. That's just the path. That's a fancy name for the path. We know that that trajectory is going to have some maximum height. Okay, that's how high the ball reaches. We know intuitively that if we throw it faster upwards, it's going to rise higher, and the height's going to be more. And we also have the range. And the range is how far that ball goes horizontally before it comes back and hits the ground. Okay, so remember that gravity is only affecting the vertical components of that motion. And the horizontal components is the ball is just moving at a constant speed. Okay, let's show what this looks like depending on what angle we're throwing this relative to the ground. So here we have a little water cannon. Okay, so you guys can see the water shooting out of this. What I want you to think about the water is as individual drops shooting out of this hose. So each one of those little drops is an individual ball that's being shot out of the water cannon. You don't have to worry about the fact that the water's in a stream. Just think about it as being little packets of water that are shooting out of here. Okay? So we are giving it an initial velocity. In this case, that initial velocity is in the horizontal direction. And so you can see that it is basically bending downwards. And if you think about this line here as being ground level, you can see that we immediately hit the ground level when we throw it horizontal. Okay? That's the same thing as me taking a ball, okay, and throwing it sideways, okay, from this level here, right? So if I throw it sideways, directly sideways from there, okay, it's just going to hit the ground immediately. So there's no vertical component we're giving to it. Let's turn the angle up on this and see what happens. One thing to keep in mind is I'm not going to adjust the water pressure at all, so the speed that these little drops of water are coming out are not going to change. We're only going to change the direction that they are being aimed at initially. Okay? And remember, the horizontal component's not getting affected by gravity. It's only the vertical component. So when we start lifting this up, I should have, wait, let me adjust this first. Nobody look. I'm going to end up shooting that wall over there if I'm not careful. Okay, there we go. Okay, so let's start off. We're shooting this completely horizontally. Once again, we're not giving any vertical component, so it's basically hitting the ground immediately, ground level immediately. Let's start turning it up. So this is aiming at 30 degrees. So we've got we now have a vertical component as well as a horizontal component. You can see that there is a range here that is basically out to about this point. Okay? And there's a height, which is coming up. Okay? The fact that we've given it a vertical component means that we've lifted the ball up so that it's going to take time for it to fall back to the ground. Okay? And during that time, it's moved sideways from the horizontal speed, right? So it's forming this arc in its trajectory. Okay? If we keep moving this up, there is 45 degrees. We saw as we went to 45 degrees that the height got bigger and the range got further. Okay, we're giving it more vertical components, so it's going higher, so it's taking longer for it to come back to the ground. Okay, so it might not be too surprising that the range got further. It went, they're falling back at a further distance than when we started. But let's turn it up a little bit more. Okay, if we go to 60 degrees, that was a little bit subtle, but you saw, if you were paying attention, that the height got higher, but the range started getting smaller. That the ball didn't travel as far in the horizontal distance before it fell back to the ground. If we go up to 75, you can see it's very dramatically, the height starts getting higher. The height gets higher, but the range is getting smaller. Okay. Intuitively, that makes sense because we know if we go to 90 degrees where we're shooting it straight up in the air, it doesn't have any range, right? It goes up and comes back down completely where it starts. So the trajectory, this, by the way, has a maximum height, though, right? The height is maximum. All the velocity is going into shooting the ball straight up in the air. Okay, it goes up to maximum height and falls down. As we start shooting it horizontally, we'll get the maximum range when it's at 45. So that's the balance where we're giving it horizontal velocity and vertical velocity. Okay, and it turns out to be the maximum time where it stays in the air. The maximum range that it can achieve because we balance the fact that it has to stay up for a given amount of time. It also has to have velocity in the horizontal direction in order for it to have any range at all. Okay? And then as we go back down towards 0 degrees, the height drops, okay? And eventually drops to 0, of course, because we're not giving any vertical component. But the range drops as well because the ball is falling. These little pellets of water or the balls are falling immediately back down to the ground. Okay? So hopefully that gives you a little intuitive feel about trajectories. And I didn't make too much of a mess on this one. Are there any questions about what we've covered so far today? Yeah, over there.
I'm curious about the example of the monkey. Like, how did you make the monkey fall when you shot
Oh, that's just the mechanic. The monkey let go. There's a magnet up there that's connected to the gun. So as soon as I fire the gun, it clicks off that magnet and it falls. So, yeah. That's a great question, though. Any other questions so far? Okay, so, over here, please.
So you said that our acceleration for gravity is 10 meters per second, and when we're doing
per second squared.
When we're doing our math, do you want any vertical acceleration to be negative then? Or do you care?
So the easy answer to that is you probably won't be doing any math. So it's good for you to know that number, okay, but I'm not going to give you any numerical problems to solve. So, but if you want to do them on your own, go for it. You're good? Okay. By the way, so if you didn't hear that question, the question is when you're using the gravity due to acceleration in math problems, should you make it positive or negative? And my answer was that you probably don't need to worry about it. So, and if you are doing numerical problems, don't get too confused on the signs. Just think about it intuitively. Okay? Which way is the velocity pointing? Which way is the acceleration going? And then think about whether your answer makes sense given that. So, saw another hand over here. Yeah. Right, yeah. So this question was asking when this demo that's not working actually worked. On when flashing. Oh, I know what's happened. The batteries run down. So let me see if I can get it. I don't think I'm going to get it to pop. So basically the question here was when the ball was shot up and came back down and landed inside of the train at the same position on the train, was that because of the horizontal velocities? Is that what you're asking? Right. So think about this in two frames of reference. So in our frame of reference, here on the ground, our friend is on that train, and the train is moving at some speed to the left. Our friend is moving at that same speed, sorry, to your right, to the right, and the ball is moving at the same speed to the right. So they already all have a horizontal component of their velocity. Okay? When our friend throws that ball up in the air, our friend's only giving it that vertical component of velocity. Okay? But the ball and the train and our friend all still have that horizontal component of velocity. So our friend is giving it the vertical component, but the horizontal components are not changing for any of them. So they're all still move at that same speed to the left side. Does that make sense? The other frame of reference is with respect to our friend. So now, so this is the power of frame of reference. Okay, good life lesson. If you can think about the world according to your friend, and from your friend's perspective, in that frame of reference, nothing's moving. And all your friend has done is thrown the ball up and down, and it's just gone up and down because of gravity. Okay? One last question before we move on, yeah? Right. So this is so the question is for the demos we are assuming we could ignore air resistance and friction, right? And so the question is if we now take into account air resistance, would we still get the same motion, or can we ignore it? And truth is, yeah, you can't ignore it, except in the case if you're an enclosed car. So if you're an enclosed bus, you're an enclosed car, then all the air in that cabin is moving at the same speed you are. And so that is no difference than when you're sitting at rest on the ground. Okay? It would be different if you're on a train that on like an open car, right? And the wind is pushing back to you. But then air resistance is another force, and then you just have to take it into account when you're looking at all the forces and the accelerations on the object. Make sense? Okay, I wanted to say one more thing, and that is I wanted you guys to have a little bit of intuitive feel about playing baseball on the moon. Okay, so here on the surface of our big, beautiful blue Earth, the acceleration due to gravity is about 10 meters per second squared. On the surface of the moon, gravity is a lot lower. It's about 1/6. Earth. So the gravity on the moon is about 1.6 meters per second squared. Okay? So there is gravity on the moon. It is acting. It's just its acceleration is only about 1/6 the level that it is on Earth. So let's think about throwing a baseball on the moon instead of throwing it on the Earth. So our baseball has two components, remember. It has its mass, which does not change. When we go to the moon. Remember, mass is a measure of inertia. That's how hard it is to make this ball accelerate. Okay? That doesn't change whether you're on the moon or you're on your Earth or you're out in deep space on the surface of a sun, getting sucked into a black hole. Okay? Your mass, well, maybe that case, we should talk about that one. But your mass is your mass. It's your measure of your inertia. It does not change. The weight, of course, drops because the acceleration drops, right? So the weight of that baseball is only about 1/6. Of what it is on Earth. So the weight has dropped for that baseball. The mass has not dropped. So now let's think about throwing a pitcher on the moon. Okay? It's about ready to throw a ball. Okay? So when that pitcher winds up to pitch, okay, can that pitcher throw that ball any faster on the moon than the pitcher can on Earth? Yes?
Because of like there's vacuum, so it's a little faster because of like there's no
Air resistance. We're ignoring air resistance. There is no air on this Earth or this moon. That's a good point, though. So we'll get back to that, because we obviously cannot ignore air resistance in the world around us forever. So one more try. Let's see, over here. You. Can you tell me why it's going to have the same speed? And what has not changed about this ball? The mass, right? The mass has not changed, so that means the inertia has not changed. Which means when you go to the moon, it is no easier to throw this ball than it is on the Earth, in the sense that you can't throw it any faster on the moon than you can throw it on the Earth. It takes the same amount of force from you to accelerate this ball. Okay? So when the pitcher on the moon throws the ball, there's a maximum speed, and that maximum speed is not going to change whether you're on the Earth or on the moon. Okay? That is the speed. So it's no easier to throw the ball on the moon than it is on the Earth. The difference, though, is going to be the acceleration due to gravity, right? It's going to fall back to Earth at a much slower rate because the gravity is only 1/6 as much. Okay? So that means even though you can't throw it any faster, you can throw it a lot further, okay? Because the ball itself and the gravity, just like that, falls back much more slowly to the surface of the moon than the Earth. That's the difference between mass and weight. Okay? Mass is inertia, weight is a force. Keep those in mind when you're thinking about the problems. Okay, next lecture we're going to pick up with Newton's third and most confusing law. So I'm looking forward to that one. So remember, guys, your sections this week and every week.